And the talk title here, maybe I should have written do simple things. This is basically going to be a little bit of a lesson of mine from about 20 years of software engineering, of what works and what doesn't work. And just generally, I like the idea of like simplicity and keeping things not complex. And so throughout this talk, I'm effectively going to share a little bit of when it's useful to build non-complex things. So the problem with software engineering is that it follows a little bit the second law of thermodynamics, which means that over time entropy and chaos increases. And so this is a lot about how to avoid that. Okay, so let's see if this works. So I've been doing software engineering for about 20 years, and most of what I'm doing is, or it has at least historically been open source software. So you might be familiar with some of the Python libraries that I wrote, and you might even maybe use some of them. So a couple of years ago I built, or 10 years ago I joined Sentry, which is an open source company that later turned into a startup, which is doing application crash reporting. I've been working there until earlier this month. And you can find all of my stuff on the internet if you want to learn a little bit more about it. In particular, this talk is in parts inspired by some of the blog posts that I did over the last 6 months. So if you want to dive a little bit more into the detail, then you can find some information there. Okay, so basically, I want to talk about this general problem that there's a huge difference between building an application and building a library. And I like doing both of those things, but it turns out that this is very, very different. When I like to build libraries, so something that a lot of people can use, then I like to build them so that they last for a very, very long time. So I'm very happy that many of the things that I built more than 10 years ago are still in use today. When you build a library, when you build something so that a lot of people can use it, you have to be rather careful with iteration. Why? Because if you change stuff over and over again, then it means that all of your customers also have to change all of their stuff again. And so there's a different kind of trade-off that you have when you build a library. And I in particular commit myself to excessive backwards compatibility, which means that I just want to support very old versions of Python if I have a choice. I don't want to break my APIs. I want to make it so that if you use my library, you're less likely to have to change stuff. On the other hand, when you build a product, very, very different rules apply. The thing with companies is that very often they don't know what they're doing. So there's obviously a difference if you build a particular software for a company that's like 15 years old and has a good understanding of what the business problem is. But when you build a product, it's not quite clear yet if the customer actually wants it. And so there's this process called finding product market fit, where you basically try to figure out, like, do people actually want to pay for the thing that I'm building? And so, particularly in startups, but also in just small companies, one of the first goals is you need to understand how to optimize your development workflow so that you can make changes as quickly as possible until you have achieved some sort of stability. And it turns out that those two things are just completely in contrast to each other. And so this talk is a little bit of the balance of these two, like how do you build something that's reusable for a long time, and how do you build something that is really aided for fast iteration. One small disclaimer here is that I will refer to complexity quite a bit in this talk, and sort of my definition of this is when something is more complex than appropriate for the size of the problem. There are big problems that need complex solutions, but most of the problems that we tend to have are small problems. And as an engineer, we're sort of very often in a situation where we overcomplicate things. So the idea here is not that complexity is bad, but that if something is more complex than appropriate, then you've made a mistake. Okay, so what are the kind of dumb things that I'm just generally advocating for? Well, one of which is Python. This is probably obvious for people at a Python conference, but Python has a lot of trade-offs. It's not Java, it's not C++, there's a performance problem. Maybe there's not the greatest typing system in the world, but it also has some benefits to it. And one of the things that it has as a general benefit is that as a language runtime, as the core of how the language works, it's a rather trivial thing. There's a bytecode compiler, generates bytecode instruction, and then it evaluates them one after another. And so it's pretty slow, but it means that because it's pretty slow, it will not get much slower. So you have almost reached the slowest part of this. And this actually is great, because it means that, for instance, adding extra instrumentation to figure out what's going on at runtime doesn't make it any slower, right? So if you, for instance, build a web service, as fast as Python will get, that's about it. And if you then want to do like fancy stuff to like inspect the process or like dump out variables or attach a debug at runtime, it doesn't get any much slower. This is a big difference for C++, for instance. If you build a high-performance C++ application, making it so that you can do something with it at runtime that's interesting is immediately going to kill all your performance optimizations. The second thing I will argue for is just build the simplest solution that works. And I will go into like why that usually doesn't happen, but that's a huge part of it. The other one is a liberal use of copy-paste. And by extension, you probably heard about this vibe coding thing, which I think is just a fancy way of saying like just use AI to generate code and use functions over classes. I'm a huge proponent to code generation with AI. And in parts, it is because I actually think out of all the things I don't like about software engineering, dependency is probably very high on that list. Over the last 10 years, I think we have become more and more accustomed to just pip installing everything. And the problem with this is that there's a world out there where everybody maintains all of those libraries. And at any point in time, you can wake up and someone made a new release, right? And so if you only use one or two functions from a library, but the library has like hundreds of them, you're still going to get all the updates of all the library, of all the functions in there that you don't want to use. And so copy pasting that one function into your library or into your own application is in many cases actually preferable. And AI code generation sometimes helps you that you don't even have to look this up because it's actually perfectly capable of writing some functions for you. Okay. This is my general favorite thing, which is constraints. I think that constraints are great and entirely underappreciated by engineers. The reason why constraints are useful is because they just close down some paths very early on, but they leave a lot of other paths open for you to explore. And I generally break them into two categories, one of which are arbitrary constraints, which are not very strongly rooted, and then there are business constraints, which are very strongly rooted because you basically bet your entire company on that. So the arbitrary constraints are often a lot of things with deadlines. So for instance, you can break your day into I don't know if you use Pomodoro timers, but that's one thing you can do is like you slice your day down into fixed intervals and you just work within that. You have sprints, you have maybe like someone says like this has to be done in a month. But the thing with these arbitrary deadlines is at any point in time an engineer can go and say like this is nonsense, I disagree with it, and what happens if I break the deadline, right? There's also this general culture wars that you have in a company, like someone says it has to be written in Python, and then someone says like, but I want to write it in Rust. But the thing with these arbitrary constraints, it's still better than not having them, because otherwise engineers like to be creative, you end up with 20 different programming languages, right? But the business constraints are much more interesting because, for instance, the business might make the decision that the product has to have a certain price point, right? And so if the product has a maximum cost that you can have before it's just too expensive for someone to buy it, that sets pretty strong engineering requirements about how it has to behave. If you want to build a business that delivers the software to customers and the customers have to self-run that on their own premises, then it sets an upper limit on the complexity of Kubernetes configs or anything like this that you want to have. Because eventually customers will just say like, this is nonsense. I don't want to run 200 services for this simple application. So these constraints are really important. And so the more you have in the beginning, the better defined your box is. But the thing with the constraints is they have to be good. There has to be, you take away an option and then you have to get something in return. So a good constraint enables opportunities. So as an example, you can have a constraint that says like, all my data has to fit into memory. This is one of the best constraints you can have because it allows you to keep the stuff in memory, right? So it gives you an option that if I were to say like, well, I have to support something that is more than I can have in memory, then all of a sudden I have to explore different paths. And I can no longer store it in memory. But if you, for instance, say like my constraints actually, it absolutely has to remain in memory, then all of a sudden I took away a lot of opportunity. Like I might want to serialize it. I want to actually use a database for this, right? So there's a difference between how you set the constraint, and it has to be valuable. You have to get something for it. You probably have seen a version of this, which is all the paths that you can take at any point in time. Constraints basically reduce the ones that you have to consider. So if you have some reasons not to go down certain paths, it doesn't really matter if there's some golden nuggets behind the rainbow there, because you have decided at the beginning you will never walk down this path. So it's irrelevant. It might even be the best path for you to walk, but you've made a decision you're not going to walk this path. And so at any point in time, if you make decisions, you can ignore all of this, because you have already declared this is not for you to walk. And this helps because it keeps a lot of conversation in engineering teams also down. The second thing with the constraints is that some of them you can define ahead of time, right? So we will come in and say like the product has to cost a certain amount of money. It has to run on Linux. It has to be written in Python. Whatever, like there's certain constraints that you can set. But then other constraints actually emerge over time. And they become these really useful abstraction points. So if you do a couple of things a couple of times, eventually we'll see some patterns emerge. And we'll see some sort of repetition. And from this repetition, you can see fixed points that are less likely to move compared to what you do initially. And this is also something you can sort of think of it as some sort of mathematical concept. And when I talk about abstractions, what I mean by abstractions is usually when you wake up and say like, you know what I want? I want to build a class. It's called builder or manager or factory or any of this. This is usually sort of where this sort of starts, right? And as an engineer, we often wake up in the morning and say like, you know what, I will build a query builder. And the problem with this is that if you don't really know what you're doing yet, you have just one single constraint, which is like, this is the one use case that I have. You can draw an infinite number of lines for it, and your abstraction becomes ginormous, right? In fact, all the lines make a plane. So it's like everything is still there. But if you instead of starting with the abstraction, you sort of copy paste your little functionality around 3 times, eventually we see like, okay, these are sort of the common ways in which I use this. Like maybe you don't have a query builder yet. Maybe you just create the queries manually in a bunch of places until you see like what are the kind of queries that you're going to build. And the thing is, if you have a bunch of fixed points, it greatly reduces the total number of combinations that you need to consider. There might still be points somewhere outside of this, right? But hopefully the first 3-4 uses of this will actually tell you a little bit what the setup is that you have. And so hopefully, if you had another one, it sort of falls onto one of those already abstraction lines that you have created. And there's a chance that it will not, right? There's a chance that you will wake up in a week and you actually define like, hey, there's a new use case, and it sort of completely stands in conflict with the API that I have already created. Well, then you have to refactor, right? But hopefully the refactoring is sort of like a smaller move than it is actually from scratch. The problem if you create the perfect abstraction from the beginning is that you will have so over-abstracted it that many of the use cases that the API can support will actually never be needed. Programmers have a crazy tendency to overcomplicate. And I think that there's a good reason for this. We often just pip install a library. If you install PyTorch, if you install Django, you're probably going to use 5 to 10% of that library, right? But there's so much more stuff in there. And so these libraries, they have to be written in a way that any kind of future problem that comes in, or all the problems that library has ever seen, have to be supported somehow, right? So the surface area that the library exposes to you is not catered to you, it's catered to everybody who has used this library so far successfully, and maybe sometimes even unsuccessfully. So when you go into a company and you start building your own code, you mostly see all of the libraries that have ever been created. And they are created in some sense in a completely wrong way for your problem, which is much smaller, right? You don't have to write code in a company so that thousands of different, like tens of thousands of people out there can use it. Your engineering team is probably between 5 to 150 people for most people. And so there's a massive tendency to overcomplicate, right? You will not have all of those use cases. And the problem with all of these abstractions is that once you have them, they make every code change more expensive. Refactoring is much cheaper for as long as you haven't abstracted. If you have a terrible abstraction and all of a sudden you said, like, I need to change the API interface, you have to go to every single place where I've used it so far and do a modification. I also have a hatred towards classes in a lot of cases because they combine the data, which is great, with the transformation of the data or what you do with this, which is a coupling that doesn't have to be coupled, right? In a lot of cases, you're better off just writing, you can still keep the class to hold the data, or you use dictionaries and basic data structure, and then use a bunch of functions that just do the one data transformation until you actually decide to couple it together. Why? Because one of the things, for instance, that you immediately lose if you attach the transformation to that thing is it makes serialization much more complicated. And that's a huge downside if you can no longer transfer your data from one process to another process. Because sometimes you have to put it in a queue, sometimes you have to put it in a database, sometimes you have to put it in Kafka, sometimes you just want to store it to disk and restore it again. And if you have your class associated with that, then all of a sudden you have the problem, what happens if the class changes? What if the structure changes? What if the invariants change? So functions have a lot of benefit, and unfortunately I think there's a tendency to underutilize them. So if there are two rules here, there's one anti-rule which is called don't repeat yourself, try. It does make sense if you build a library, but in a company usually it doesn't make sense. And the better rules are YAGNI, which means you ain't gonna need it. So like, don't build the abstractions until you need it. And the second one is called the rule of 3, which I would sort of describe as you copy paste something better 3 times before you start building an abstraction. There's some really good books from the people that actually came up with those rules that are worth reading. And just to summarize this a little bit, and this is maybe not just a summary, but also sort of like maybe a little bit of sort of like a thing on this. Junior engineers think abstractions and junior engineer thinks that constraints are shackles that should be thrown away. Experienced engineers see them as a source of clarity and direction. When you go and you work with people that are sort of new to the industry, very often, like every time you sort of like, it has to be this way, there will be, but why? Can it just not do it this way? And just you learn over time that like having a smaller box to operate in actually gives you a lot of freedom, which is really ironic. Because constraints narrow the problem space greatly. Okay, but then sometimes you do need to build abstractions, right? And you have to build for reusability. So I will start this with saying like, probably you don't. But in companies, you will have a certain type of reuse. So think of a framework like Django. There are thousands of people who wake up every morning and build something new with Django, right? So there's a really high number of people that start from scratch. And they use every API over and over and over anew. How many times does your company start a new product? Maybe once a year, best guess. Sometimes you have little side projects where you hack around, but like the total amount of times you're going to start something again is very, very low. It's unmeasurably low for a lot of companies. And if you do create projects over and over, then you're sort of in a different business. But in many cases, you don't actually start new projects all the time. And so the actual use case that you most likely see when you do want to build for reusability is not to start something from scratch, but to add a new function or a new functionality to your already existing code base, right? And some of those code paths are immediately visible. Like if you have a web API, you're going to have multiple endpoints, all of which return some form of API. If you want to see what's going on, you will send logs, you will send metrics. You will do this over and over in your code base. If you need to do some background work, you will have the ability to create these background tasks. So these are all these sort of very obvious places where it actually makes a ton of sense for you to have an abstraction in place, even if you already use a framework, right? Even if you use Django or something and you return HTTP responsive with serialized JSON all the time. It's actually better for you to make a utility function that generates this because they have one place where you can do logging, debugging, all that sort of stuff, right? It's very useful to wrap this kind of stuff. But you will most likely not build a library, even in a company. And this is because you can think of a library as a service boundary. And it is very critical because it does mean that the library where you write your usable code and the main application where you use it, all of a sudden they're two distinct, separately moving code bases. And if the interface is not stable, then you create churn. What does it mean? It means that I now discovered that the function that I've created in my library is insufficient for the new use case that I need. And I have to change it in a way that is no longer compatible with the things that I have done before. So if it's a library, if it's a true library that you pip install, that you install separately, you're going to end up with a very annoying situation where either you have to now change the library so that does the new thing and the old thing, so they can step-by-step move the new code over, or you have to adjust the interface in a way that it can be both supporting the old way and the new way. What you cannot do with a library is to say, like, I'm going to change the function and simultaneously change all the uses, because at that point I have to move them in lockstep. And you can't really do that because, like, how are you going to do this upgrade? You have to do like 2 pull requests and try to like simultaneously merge them at the same time, right? It requires this lockstep movement between them. And in most cases, what you actually should be doing is you should have it in the same place and just a module in your application. So rather than trying to separate it out entirely, you keep it there. Why? Because you can actually make this lockstep movement. You have one commit that changes both the interface and all the users if you have to. So the idea is initially you will only ever start creating a library if you no longer change the code in some sense, right? Like if you have achieved peak stability. So the idea first is that you modularize your code base. You have your crazy monolith with all the terrible code you have written so far, but you can take some of those pieces out, separate it into an internal module that you can use that hopefully never grows too large. And then eventually, maybe you want to create a library from it. This is also just generally why I recommend monorepositories, where you have one repository for all of the hundreds of things that you have at your company. Fortunately, GitHub makes this very hard, but I don't know how familiar you are with this, but all of Google, all of Facebook run from one single repository. Like there's just one. Why is this great? Well, it's great because like there's just one thing you need to check out. There's one thing that moves in lockstep. I can travel in time back and forth, and I will always find the perfectly reproducible set of what the world looked like at this point in time. And this also simplifies the tooling. There's just one place I have to look at. And then I modularize within my repository. Okay. This is about, now that we have understood that we should probably not build libraries, some other stuff you can do to actually be relatively productive. I will go back to the second law of thermodynamics, which is chaos increases over time, entropy increases. Not only does entropy increase in the code base, so like by definition, if for as long as changes go into the code base, it will get more chaotic. The only way in which it doesn't do that is if you put extra energy in to hurt the chaos, to reduce it, right? To bring it back to order. And what's kind of crazy about code bases is that you have actually irreversible chaos that you can never get rid of anymore. Because the chaos is the service boundary to the external world, and someone will have already started using that. So in a lot of applications, you create network boundaries. You can create an API where someone else, your customer, will start sending you stuff in. And once you have created this, you have made a contract with that other person. You can be not nice about it and say like, well, I made a mistake, so I'm going to remove your API. But if you keep doing that over time, eventually a customer will no longer pay you because they're like incredibly frustrated by the churn that you're subjecting them to. So particularly once people start using something externally, there's a fixed point that is very, very hard to undo. And one of the big problems with this sort of chaotic stuff with code bases is that there's this general tendency to say like, well, because computers got so incredibly efficient, we don't have to be particularly good anymore, you will not notice. And that is actually true. Like you can write terrible code and it will still be fast. And you can, and particularly like someone who is maybe not an engineer will very easily make an argument that there is no point of maintenance because in 6 months I can just buy a faster computer and it's perfect. And computers are in fact getting faster. What is not getting faster are the humans that need to work with it. They're getting maybe a little bit better because now they can use ChatGPT and stuff like this, but more or less we are constrained by our ability to understand what's going on. And so the more chaos you have in a code base, the longer it takes you to change anything. And this is actually what kills all your happiness in engineering, is if the things that you want to do are limited by stuff you don't want to do, but you have to do, and those things take a long time. For instance, if your test suite runs for more than 30 seconds, and most test suites probably run in the minutes or 15 minutes or worse, it's not happy. You're not happy. You're making a pull request and then you have to wait, right? Like the perfect time for your test suite to pass is under a minute. And one of the problems with test suites in particular is that why are they getting slower? Well, they're getting slower because like as you're building more stuff, there are more tests. But that's not really what kills it. What kills it is that very often you have per test overhead. So a very common problem is that you create a web application and every test creates a database, destroys a database, creates a database, destroys a database. And you could say like, okay, maybe this takes like 2 milliseconds and that's fine. But you also have to consider like how long it takes you to create and destroy a database is proportional to how many database tables there are. So as your application gets more complicated, it also creates more database tables. And then eventually the per test overhead in itself scales linear. And so then you have something that grows worse than linear because you're creating more tests and each test is going to take more time. So any time spent making the per test overhead lower is a time perfectly well spent. Particularly if you have a large enough engineering team, you can actually measure how many tests you're running. In a lot of companies, you're running years of tests every day, which is absurd. The other thing is like if your deployments take long, like the act of taking the code that runs and shipping it to production, if that takes too long, one of the biggest consequences of this is not just that you have to wait, like you have to wait for tests, you have to wait under stress, which is a problem. And then all of a sudden, you're less likely to do risky changes. And you want to do risky changes. You want to risk stuff. If you, for instance, your deployment takes 15 minutes to go to production, it means that you're not going to do any risky changes if it also takes you 15 minutes to roll back. Because imagine your website is done for 15 minutes or 30 minutes, right? You don't want to do it. So eventually, the slower the deploys take, the more you front load all the risk management in terms of like acceptance tests and like someone maybe like tests the website manually, stuff like this. But if your deploy only takes 15 seconds, well, then worst case, it's broken, I roll back, everything is happy, right? I can even automate this process. Like if it's broken too long, I just automatically go back to the old version. And what happens in an engineer's brain is actually the most important part, which is like, if you know that everything takes so long, you're going to feel much more mental burden in all the changes that you're doing. And the consequence of that mental burden is that if you need a second human to look at the pull request, to sign it off, that human has the same mental burden. And in a lot of engineering teams, one of the problems is that you actually it's not just that the PR review, the pull request review takes too long, someone to come in and say like, this is good, this is bad. It's that nobody shows up. They only show up for the small changes because someone already knows like, oh, I'm going to have to spend at least half an hour there and I have my other problem, and switching from my problem to the other problem in itself takes me like 2 minutes and unhappiness, and maybe I'll just go for a coffee first. So all the big changes that you want to land will never have a human show up in the time that you want it. And this gets worse and worse the harder, more complexity is in the pull request. Like if there are situations where you can no longer run the pull request locally because like it's too complicated to do that, so then the human has to just look at the code. So if there's an upper bound of how much change you can do, eventually they're like taking so long that you will be like not wanting to wait anymore. So you push another commit into your pull request. And so then like it just grows. The pull request becomes bigger and more complex, and the other human also just no longer want to do with it. It scales terribly. So any sort of complexity in the system makes code review much, 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 much harder. And then one common problem with a lot of situations is that if the task of adding stuff to the code base in itself requires extra steps to be done, then people will also sort of hack around it. And so an example here is you might be using something like Avro or Thrift or gRPC or Protobuf. Those are systems where you generate a new schema somewhere, and then you have to do some code generation. And if the act of adding something to that is not sufficiently automated, then it sucks, because now all of a sudden you have to do 5 steps every time instead of just it running automatically. So all of these common additions, if they have to happen over and over, eventually just get very, very frustrating, and nobody likes working on that code base anymore. I like to think of engineers as electrons. They go the path of least resistance. The problem with the path of least resistance is that very often you have two options. One is the quick and dirty one, and the other one is the nice one that takes too long. And then take a guess which one the engineers will walk. They will go to the hacky one, right? Which is absolutely perfectly reasonable in some ways, right? And so you have to make sure that the right path to go is about closest to the optimal path to walk, right? Like just shooting down on engineers and pull request reviews, like you should have done the shitty one, like the slow one, the one that's like blessed by the principal architect. That is just, it will not work. Like it will work for some period of time, but eventually everybody's unhappy and just leaves. So you have to make the right path, the easy path. There's a little bit of the reiteration of this. If the cognitive load is too much, then it just takes too long to get these pull request reviews. And the one that I think is the particular one is like if you're in a situation where you can no longer easily run the code that's being changed, you have such a hard time as a pull request reviewer. And I would guess, at least based on some numbers that I've seen, that 95% of pull request reviews are never actually tried, like they never run. And the only reason this number looks so good is because for certain types of applications, there's like auto deploys and you can click on it and you can see what it does. But if you work on data pipelines or anything like this, it's very likely you just look at code, you never run it. You just hope that the test coverage is good enough to understand that this works. But in some situations, you cannot even check it out and run a test locally, so that the test fails in CI. You see like, okay, great, invariant failed, assertion failed. And then and for some reason, for the one person, it passes locally, but you're never going to try it anymore because it takes you like 15 minutes to try to also get the test running. So you just maybe tell the other person, like, try this, maybe this does it, and then that person for whom the test passes locally, now all of a sudden you're like debugging CI, right? You're like, for some reason a test fails in CI, but it runs locally, so you're just doing these changes over and over, and each one of them might take 5 minutes, so like an entire day is wasted of trying to make CI pass. And then you eventually learn, well, the actual reason it passes locally and it fails in CI is because there was order dependence, or there was like different randomization going on, or like you had a different version running of the same thing. Like there are many different ways in which you can go. And if you're no longer in a situation where the system that you have running locally looks the same as the system that you have running in CI or in production, then you're in what I call like general like emergent behavior, where your system stopped being deterministic and it turned into an organism. And it's like a patient that has some symptoms, and you can try to do some stuff with it, but it is no longer a computer, because computers are normally relatively deterministic. And the harder and more complex the systems get, the worse and worse it gets. Particularly when you work on web services, they are distributed by definition, which means that there's multiple things talking to each other, and they have their own little lives. They have their own little behavior. Distributed systems in particular, if they're not herded well, they will turn into really, really complex organisms you don't understand anymore. There's a concept in control theory called observability. And the simplest way of understanding observability from that point of view is that if there's a thing happening, the output of that is enough to walk back and understand the system at any point in time, right? So you basically can look at just the output of the system, and you can, by walking backwards to the starting condition, understand every step in it, which is the most perfect system you can have, because it means that you only need to look at the output and you understand what happened. No computer program works this way, because they do all kinds of random stuff internally, and the only way to get any sort of understanding is to log everywhere what happened along the way, right? Because like otherwise, maybe the act of creating this, like go to the database, run a bunch of queries, produce some transformation, create an API response. There will be really important things that are happening along the way that are not visible in the API response. So just seeing the API response in the test will not tell you what happened along the way. And this is already annoying during development, but it is very, very frustrating when you actually have a service that has to run, a bunch of people are using it all the time, and the service is unavailable. Something happened. And all of a sudden, everybody stands in a room and nobody understands it anymore, because you already, under normal circumstances, didn't understand it. But now it's doing weird stuff, and now you have completely lost the plot. And with increased complexity, the likelihood goes up that the only reason the incident ends in the first place is because it magically recovers. Like it somehow did it itself. Like it didn't have enough time to actually go in and do something magical to make it quicker, to recover quicker, to find the problem. in a lot of cases, distributed systems just magically heal themselves. Like, we don't know why it broke, we also don't know why it fixed itself. And that's not a good position to be in, because it makes you unhappy. It makes you look at this and okay, it's great that it works again, but why? Do I have any guarantee that this will not wake me up at 2 o'clock in the morning, pager duty goes off and tells me, well, the thing that happened last time during lunchtime now happened at 2 o'clock at night. This is just not a situation I want to be in. Like, this eventually just drains you out. So there has to be a mechanism that you use to reduce that overall complexity. Because once there's too much of it, the energy that you have to put into it is just too much. So if you don't have a great, crazy code base yet, the loop looks something like this. You build, you copy paste a bunch of stuff, or you leave it alone. And then if it sort of becomes a little bit too complicated, you start to abstract. You take 20, 25% of your time, and you try to do two things. You either throw away stuff, you don't leave stuff around that should not be used anymore, or you try to put this extra energy in to reduce some of this complexity, right? If someone has copy-pasted something around 15 times, that was probably a mistake, and you should be abstracting it, right? That's also not the right solution. But there has to be this extra energy going in to bring it back to some sanity. This is basically almost the entire presentation. But I have one sort of last thing before going to the question, which is I just want to give you really actually only just one idea. It's the only piece of code that I have, which is in Python in particular, one of the best and most underutilized systems is what's called context variables. They basically allow you to bind information with the flow of execution without you having to pass it from function to function. Because one of the problems that you often end up with is that you now need to log out useful information. You now need to share something useful with everybody. Or let's say you build an application that has to uphold security guarantees. There's a current user, that user might have admin access. It might be part of a different organization. You might have to validate that the right thing is happening. The way you usually do is you pass this information from place to place to place to place. And that's useful. That's a good way of doing it. But the problem is, what if you need to uphold or log or do any of these operations very far down into a call stack? And so context vars basically you can think of them as like hidden function parameters that flow with every single function call. And so this is a very simple example. You can create this application context. You can, for instance, say like, my current user, I always want to remember. Why is this useful? Because you really want to know who the person was that broke your app. Not because you want to like email them and tell them, don't do this again, but because knowing who broke it allows you to go through the log files and figure out like, what did they do? Like, what did they manage to do in the system that you shouldn't have done, or that they shouldn't have done and that your code should have protected against? It's also great because you can send an email and say like, hey, we fixed your problem. You should also remember if you have a multi-tenant application where like multiple people, multiple projects go through the same code base, you should always bind your tenant so that you know, as an example, if you run a database query, that you constrain it to that database. You don't accidentally give one customer access to another customer data, right? And so then you can have a function called getCurrentUser that you can call at any point in time, and you know who the person is that you're working with. So this is what this looks like. In this case, it's a web thingy. You create this application context, you bind the current user, and whoever calls the log method later can actually get this current user and attach it. This is such a simple idea, but it's so underutilized. And it is so important because it means that you can basically, you don't have to touch so much code to uphold these very basic guarantees. And having assertions all over the place that guarantee you that the system still looks like you expected is really, really important. You don't want to write code that for 6 months did something that you think shouldn't have happened, but you never checked that it actually did the thing that you wanted it to do, right? And for instance, if you have a database query thing that's sort of like, I want to load all the data for this organization, you can check that the organization passed is the organization that is actually the one that's handling the current request, right? And we had a lot of incidents over the years with security issues where like someone didn't pass the right information on. So this is just this one idea that I want to give you, which is like bind all the relevant information, like current user, current data pipeline, current whatever is going on, like what encapsulates the execution of your thing. hold it somewhere and then assert along the way that it still is exactly in the state that you want. Because it's a very useful constraint, and it brings some sanity into the whole thing. And with that, I'm basically done.
I'm not sure if I understood the last concept you showed, the context variables, but it looks a little bit like global variables. Why doesn't it have the downsides of global variables?
A global variable is basically a thing that has the same value for everybody who's looking at it. Context variables are following the logical flow of execution, which means, for instance, that if you have, what do you work with? It's like web applications, or like what's the kind of thing that you usually work with?
More the data part. Like
okay, so if you have let's say you have something like a utility function, a data pipeline, or something like this. Depending on how it's set up, the same process can work on two tasks simultaneously, independent of each other. Sometimes it's set up that the process only does one thing at a time, and then a global variable would theoretically work. It's just ugly. But very often what you have is that there's one function that does a certain transformation, and simultaneously that same function is called another time in a different thread or in a different coroutine or whatever, right? And so a global variable would mean that they get in conflict with each other. Context vars travel with every function call. So if one function calls another function, and you then could even start a thread and you could transfer this context into that, it means that they are, in some cases, they're called execution context or flow context. In Python, they're called context variables, which is unfortunately a little bit too generic of a name. But really, it travels with every function call, and they're fully isolated from each other. So you can get them from anywhere for as long as they're set, but they can have different variables for different people. And if a web application is very common because you have something like Django API routes or fast API request routes. They might be, each one of those routes can prime the context variable differently. And so you, from that flow onwards, you can check everywhere, like, where am I coming from, what's my request, and so forth. But it looks different for you than it looks for the other person from a different HTTP request or data pipeline.
So it's really doing the same as if I would just pass it around.
It is exactly the same as you would be passing it. It just magically happens behind the scenes.
Okay, amazing. Thanks for the talk. Really nice talk.
Hi, thanks a lot for the talk. So throughout your speech, I think I understood that it's better to minimize the amount of abstractions, but are there still use cases where you'd rather use an abstraction?
So basically, if you do something more than 3 times, then the abstraction is sort of where you would do it. And I think I had, why did I have it here? No, that's the wrong one. I think I have it here. So basically, this is sort of the canonical example for a web application. Each one of the API requests will have to access the database, send a query, log some stuff, serialize HTTP responses. That's why you would abstract. And then the abstraction pays off very, very quickly because you already know that today your application is 10 API request endpoints. And then maybe like in a month it's going to be 20. Like you can sort of almost plot out how complex the application gets, and they all will look more or less the same. Right? So there it already makes a ton of sense. And database queries in particular, a huge benefit of it. Like one of the problems of abstractions is that sometimes you get a framework. You usually get a framework. You might use something like Django, you might use something like Flask or a fast API. In a lot of those cases, the way you work with the database is in itself already abstracted. But you kind of want to control the abstraction. So often these frameworks give you like plugins so you can hook in and do some common stuff in there. Because one of the things, for instance, that's great about abstracting database queries, for instance, that you can log them. You can figure out how long did that take. You can look at them over time. You can figure out like why they're getting less and less efficient, right? So being able to have like common abstraction points is actually useful at that point. But you should only really create the abstraction once you have already seen that you're going to do this more than once, more than 3 times actually, right? And the risk of getting abstraction wrong is very high. So the canonical example of the wrong abstraction is when you do database queries all over the place, and you're a big company problem, right? You're so big that your database is too slow because of too much throughput, or it has too many database tables in it. Then you need to do what's called sharding or partitioning, which basically means that you break down your huge database into smaller and smaller databases. And then you have to pick like which part of my application goes into which database. And if you have created the wrong abstraction, you will not have enough information to route them to different places, right? So you need to understand a little bit the problem ahead of time so that your abstraction is created correctly. Because if you, for instance, haven't built for sharding in mind, but your problem is eventually sharding problem, then you will have to go to every single database query you have ever made, and you have to add the right routing information in it so that you can actually do this kind of stuff. But basically, it comes down to how often are you going to do something. And then you should build the abstraction when you have seen yourself already doing it a couple of times.
Okay, thanks a lot for the answer.
Hi, quick question. Why using, let's say, LLMs or some sort of vibe coding is necessarily bad if you're just speeding up some basic things? Or is there a particular threshold that you're saying, okay, if that gives you quite a good scaffold, up until this point you would use cursor or such things?
I don't think it's bad. I use it a lot, and I think people should generally be using it more. The benefit of code, so I mean, like, you should not turn off your brain, so there's a risk of that, right? But I think we've sort of like almost overcomplicated the act of engineering. Most of the stuff that we're doing is not actually really engineering. It's just putting a bunch of like text characters on a page. And they look very similar, right? There's like the hardcore complicated, like you need to create some sort of like noise algorithm. You will be happy if you have that problem every once in a while. Most of the time, there's a bunch of ifs, there's a bunch of loops, there's a bunch of like calling different kind of stuff. And AIs are very good at generating this code. And one of the reasons why I like the idea of code generation with AI is because you're less likely to use a dependency. At least if you have an option to say like the cost of, like there might be a function in there that does something interesting. Like for instance, I wrote about this recently, getting the size of the terminal, right? The total line that you would have to write from scratch to do this is about 20 lines of code. The terminal interface hasn't changed since 1976, right? It's a very, very long time. AI generates me this code perfectly. I can put it in there, I can forget it, it will be there, and I don't even have to look it up and do complicated stuff. There's a library, this is not from Python because Python is built in, but there's a library in Rust which gives it a terminal size. Over the last 2 years, it had 50 updates. None of which because the way in which you get the size of the terminal changes, but because it has dependencies in itself and they change, and so you have like, you're going down this permanent churn. And so AI sort of gives a little bit of this power back of like, if I only need one function, I can I keep hitting this, putting it into your code base and just leave it there. Right? It's a function that functions and it doesn't change is not dead. It's just a very good function. And so that's why I like this AI stuff in general, is because like it is more likely to increase the number of small utility functions in code bases rather than people sort of constantly going to dependencies. Thank you.